Okay, so hello everyone, my name is Dario and I'm a PhD student at ETH Zurich. I'm going to present Coyote, the system we built with which we try to answer the question to what extent the traditional OS abstractions make sense in the context of an FPGA as part of a hybrid computing system. Now, to give a bit of an insight, hybrid computing systems consisting of a CPU coupled with an FPGA are gaining a lot of traction, especially in data centers and in cloud environments. Examples like Amazon F1 instances, which you can rent. Microsoft does a lot of in-house in-network data processing with Catapult. Intel has a few iterations of the HARP already, and so on. So they're definitely here to stay. And because we believe in this as well, we actually built one of these systems ourselves at ETH. It's called Ensign, and you can check it out under the link there. Now, these systems are able to provide much more flexibility, often more performance, all at lower power consumption compared to more conventional systems with ASICs or GPUs. So why don't they appeal to an even wider audience? Well, the major problem is their complexity. So on one side, you have a CPU, on the other, an FPGA, which is notoriously difficult to program, and then you actually have the interaction between these. Maybe some volatile or non-volatile FPGA side memory, network. All of this adds to the overall complexity. The major problem is the lack of proper abstractions that we usually find in the CPUs, for instance. So for this reason, there's been quite a bit of recent work which aims to apply ideas from operating system design regarding scheduling, allocation, management, isolation to these FPGA-centric computers. And so far, most of this work has been optimizing a particular subset of functionality only. However, what makes these OS abstractions so challenging to implement is the interaction between all of the functionality, as these abstractions are actually very closely interdependent. As an example, the virtual memory depends on the physical memory management. The scheduling would need to take into account stateful services. Everything depends on the execution environment, and so on. So because of this, rather than looking at isolated abstractions and limiting the FPGA to a subset of its features, with Coyote, we examine the consequences of a more complete general purpose approach. So Coyote provides a complete minimal core set of essential features above which other services can be based, just like the microkernel. So I'll quickly go over the foundations of the system. So Coyote splits the FPGA hardware into static and dynamic regions. Now, a static region it provides the base functionality for the rest of the FPGA, and it is always online. Now, it is static during a single deployment, but is also highly customizable during compile time and can accommodate various system configuration scenarios. Now, dynamic region is the basic mechanism for the sharing of the FPGA applications, and it is split into multiple smaller virtual FPGA regions. Now, one feature of the Coyote is that each VFPGA is further split into the untrusted user logic, which is a partial bit stream of an arbitrary user application written in any of the common RTL or HLS languages, and then the dynamic wrapper, which holds the virtual context of the VFPGA and importantly provides the interfaces to the rest of the system. Now, Coyote also implements much of the functionality which is not on the critical path in the software. So the software consists of the Linux kernel driver, which handles most of the management, so memory allocation, control plane, servicing of the page faults, and so on. The runtime scheduler, which schedules the submitted user tasks. And then finally, the high-level API, which is exposed to the end users and which allows the interaction with the system. Now, moving on into the abstractions, the basic abstractions used for multiplexing and virtualizing the CPU resources are processes, threads, and tasks. On the FPGAs, things are fundamentally different since we don't necessarily have CPUs or cores on which to base these abstractions. So instead, the FPGAs use spatial partitioning of the FPGA fabric and partial reconfiguration, where certain portions of the FPGA logic are swapped on the fly without affecting the operation of the rest of the FPGA. Now in Coyote, we combine both of these approaches, and we provide a multitasking abstraction for a set of independent and isolated VFPGAs. Now, importantly, VFPGAs are equivalent, and they can be time-shared between multiple applications. Now, processes also serve the purpose of providing a standard execution environment. So an application compiled for one process should in theory run in another one as well. Now, on the FPGAs, standard execution environments don't really exist across the platforms yet. So often porting the applications is far from trivial. And on GPUs, we have OpenCL, we have CUDA, and Vitis tried something similar for the FPGAs with Vitis. Xilinx tried something similar for the FPGAs with Vitis. However, what this doesn't take into account is that FPGAs are not just pure computational devices. So they can also perform some I/O, maybe for external storage. They can maybe do some in-network data processing, which is one of the major selling points of the modern FPGAs. Now, because of this, in Coyote, we provide a standard execution environment with a single user logic interface, the ULI, for every application. And this defines a clear set of interfaces for the interaction with every part of the system. Now, the access is fairly low level through well-known protocols like AXI and then simple queues, which are quite similar to kernel pipes used for the IPC. Now, the major benefit of the ULI, besides the obvious portability one, is that further services can easily be added through these common interfaces. And as an example of this, we integrate open source TCP/IP and RDMA network stacks without much extra overhead. Now, scheduling on the CPUs can be preemptive or non-preemptive. Preemptive scheduling requires the ability to interrupt the running process, stop the execution, capture the state, do a context switch, and all of this without the process actually doing anything on its own. Now, when the FPGA is capturing the state of the FPGA logic is very difficult. And although there's been research in this area, the overheads are massive. And essentially, you need to capture the state of every block RAM, every URAM, every flip-flop, every register in a DSP. And the basic mechanisms to do this just don't exist yet. So for this reason, Coyote implements a task-based approach where tasks are first submitted to the runtime manager and they run until their completion. Now, if a task misbehaves, it's kicked out. And for the scheduling, Coyote employs a modified priority queue-based scheme, which reduces the amount of unnecessary partial reconfigurations. Now, it sorts the submitted tasks based on their target bitstream image. So if two tasks are targeting the same bitstream image, they will be stacked one after the other, thus removing the expensive partial reconfiguration in between. Now, Coyote deliberately avoids preemption, which some related systems like Amorphous or Optimus implement. Now, these systems expose explicit preemption interfaces to the user applications, requiring their cooperation. And one reason why we don't go for the preemption is that traditionally operating systems can't always trust those user applications. Secondly, the preemption would also need to take into account services like network, so capture and restore the state of these as well. And again, going back to that initial line in this slide, the basic mechanisms to capture the state of the FPGAs don't exist. So this is quite difficult. Now, virtual memory is another important abstraction. It solves several critical problems, and it tends to be ignored in the FPGAs, or expensive address translation is handled in the host. Either way, you can't just pass pointers, virtual pointers, from the user space to the user logic in the FPGA freely. And this actually lowers the programmability quite a bit. Now, Coyote implements a flexible approach to virtual memory, which gives us multiple ways to access both the host CPU and the local FPGA memories. And rather than rely on a single FPGA MMU or IO MMU, we actually integrate separate software-loaded TLBs in the wrappers of each vFPGA. And this gives us, first of all, the capability to separate the address spaces, and secondly, to efficiently mediate accesses to both of these memories. Now, the flexibility also gives us the ability to implement additional memory models on top. And we choose to implement the NVIDIA, the unified virtual memory, which is similar to the one NVIDIA uses for their GPUs. Now, the usage model of this memory is either the one where data is accessed on the host and then transferred to the user logic, or the one where data is first demand paged into the local FPGA memory and then transferred to the user logic. Now, this model has a lot of programmability as it removes the explicit need for memory management and data movement from the users. Now, as mentioned, Coyote integrates high-performance 100G, TCP/IP, and RDMA network stacks. These are multi-tenant and are shared between all of the VFPGAs. And importantly, they abstract away the complexity of the physical network interfaces and provide a much more simple net connection-oriented ones to the user logic. Now, similarly, Coyote implements memory stack abstraction. It hides the complexity of multiple FPGA memory channels by using striping, which preserves the simple one-channel interface, but optimizes the bandwidth across all available channels. It also adds quite a bit to the portability, as the user logic doesn't really need to care how many channels are attached. And further services along these lines are easily possible over these common interfaces, so external storage, maybe some external accelerators, and so on. Now going to the evaluation, so Coyote currently supports a range of Xilinx development and data center boards, and all the tests were conducted on the Xilinx VCU118. Now we do plan to port Coyote to some of the Intel boards as well, and we're currently working on a port to our own Ancient system. So depending on the configuration, so the number of FPGAs, the depths of the credit-based queues, number of outstanding transactions allowed, sizes of the TLBs and so on, Coyote uses 15 to 25% of the FPGA resources, which we actually find quite acceptable, especially if you take into account the modern growth trends of the FPGAs, and how much we are willing to for instance, to give to the operating systems on the CPU. Now I'll move straight away into the real-world application. So we compare Coyote to some of the commercial systems out there, namely Amazon F1 and Intel Harp. Now, what we want to show is that Coyote is a viable alternative to these systems, and that it comes with negligible performance cost. So the application we implement is gradient boosting decision trees. Now, when we focus on inference, now this is a form of supervised machine learning, which is used for classification and regression. And the inference on the FPGA is done by first loading the model onto the FPGA on-chip memory, and then actually the data is fetched from the host, the inference is computed, and the results are written back. Now, all of this is done simultaneously, which allows us to actually hide the computation behind the memory accesses. And on the graph here, we show the throughput of the computation. Now, the Amazon F1 uses a strict GPU compute model, which comes with a lot of transfer overheads, and for this reason, it's quite a bit slow. Design on the Harp runs at lower frequency, otherwise the performance is quite comparable. One feature of the Coyote is that data can be easily received from the network, or the results can be sent over the network quite easily. Now, what we can see from the graphs also is that Coyote achieves comparable or better performance of these commercial systems, whilst providing all the abstractions that these systems are missing. Now, we also measure the penalty that you have to pay each time you do a swap of the logic in the FPGA. So the graph on the left shows the partial reconfiguration time, depending on the size of the region in the FPGA that is being reconfigured. As we can see, the partial reconfiguration is still relatively slow, and this is the limitation of the current hardware. Even this performance is far from trivial to achieve. What this means is that the partial reconfiguration is often the most expensive part of the computation. And as an example of this, we run a simple test case where we submit 4 different small tasks, each 100 times, to 3 different FPGAs. As we can observe, without the scheduling, the overall execution time is dominated by the partial reconfigurations. Even with our simple scheduling algorithm, we are actually able to drastically reduce the overall execution times. And of course, further optimizations are possible, but they are beyond the scope of this paper. Now, we also evaluate the fair sharing behavior of the system, a key requirement in most of the cloud deployments. So we run 4 different applications. The first one is the SHA-256 cryptographic hashing function, which is compute bound and uses low amount of memory bandwidth, so thus it scales perfectly. In contrast, we have the AES encryption in counter mode, which is highly parallelized, and it actually has to share the available memory bandwidth. We also run 2 more complex applications, the hyperloglog cardinality estimation, and then the k-means clustering. Now, in each of the experiments, we run a single or multiple applications side by side, and all of the experiments are accessing the data in the host memory, except the k-means, which, due to its iterative nature, actually has the capability to use most of the bandwidth or higher bandwidth that is available from the local FPGA memory. Now, we show the throughputs for these applications, and when multiple applications run side by side, we show the average throughput and the mean average deviation to assess the fair sharing. As we can observe, the sharing in the Coyote is indeed fair. And you can check out the algorithms and implementations, the comparisons with the CPUs in more details in the linked paper below, the linked papers below. Okay, so finally, we will examine 2 abstractions that we implemented. So the first one is the hiding of the memory FPGA channel complexity with striping. So in this case, we run a simple DRAM to DRAM copy. And to evaluate it, we have 3 different scenarios. So the first one is the single channel only, which is the baseline. The second one is 2 channels, which actually reads from one channel and then writes to the other channel. And this is the optimal case and requires the explicit knowledge and interfaces to both of these channels. And then finally, we have the striping abstraction, which does the optimizations in the background. What we can observe is that striping preserves the simple one-channel interface and portability, whilst actually providing a near optimal performance. Now, the second abstraction is the GPU-style unified memory that we implement, and this is a form of distributed shared virtual memory. So whenever a user logic tries to access virtual locations in the local FPGA memory, which are physically not there, it actually generates a page fault that is serviced by the driver, which also initiates a copy of the data from the host memory to the local FPGA memory before everything can proceed. This simplifies things a lot and eliminates the need for explicit memory management from the users. Now, the overhead in this case actually stems from the initial page fault. However, the local FPGA memory is often used in iterative processing. For an example, the k-means that we showed before. And in this case, actually, this overhead can be really nicely amortized over all of the iterations. So the graph here shows this overhead in the context of an application. So for the low number of iterations, we can see that the overhead is quite high, suggesting that this model might not be the best for streaming applications. However, as the iteration number rises, we can see that the overhead becomes quite negligible, which is actually the intended use case for this abstraction, ML training, for example. Okay, so hybrid computing systems are definitely difficult to program. There is an evident need for proper abstractions to make them more approachable. Coyote demonstrates that to find the right set of abstractions for the FPGAs, you need to look at a complete picture, and it shows that a reasonably complete set of OS abstractions can map well onto the FPGAs. Now, Coyote is open source, and you can check it out under the link there. And also, we would like to thank Xilinx for their generous donation and equipment. And that's it. Read the paper, and thanks for your time.